Yeah. So a little bit of a like preface to the talk. What I'm mainly aiming to do here is kind of give an overview of some of the distributed inference techniques that we support in vLLM. I know we have a bunch of people that have like varying levels of familiarity with these techniques, but my main like target audience here is folks that you might be using some of these techniques, or you might be wanting to serve some of these larger models, and you just want a little bit more of a peek into how that exactly happens. And I think more than that, like some actionable feedback and items that you can take to kind of get some intuition around your deployments and how to kind of maximize the performance when it comes to some of these distributed settings. And so we are fortunate to have, Michael, Tyler, and a bunch of other folks that are super familiar with a lot of these techniques in the chat, and especially the vLLM architecture when it comes to V1, for example. And so feel free to ask some questions in the chat. At the end, we can take some questions verbally as well, but feel free to ask in the chat right away, and they'll be, I'm sure, happy to take a look. So that being said, let's get started. Okay, so we'll start with a brief motivation and a very quick look at the vLLM architecture, and then we'll go into a kind of deeper dive into some of these parallelism techniques, a little bit about how they're implemented, and some of the trade-offs as well. I think that's the most interesting. And then we'll conclude with some actionable advice as well. Awesome. Yeah. So I think this is kind of a problem that a lot of us have faced at some point in time, right? We're trying to serve a model, and then we get that dreaded CUDA out of memory, right? And then at that point, you're kind of just bummed. You don't know what to do. And one of the things you can do is, I should say, you can always reduce precision, right? So nowadays, FP8 is a very common D type for serving models in, and indeed, there's a lot of research ongoing to even lower numbers of bits, right? And for models such as DeepSeek R1, what we want to know is how do we continue to effectively serve these models even when they're going to, I guess, 600 billion parameters or even beyond that, right? So there's DeepSeek R1, there's Llama 405B, and that's really our primary challenge, right? So this is one way to do it, is to reduce the number of bits that you use to serve the model, but keep in mind that this has a couple of issues with it as well, right? The first issue is that accuracy is potentially affected, right? In terms of you're not going to have a complete match with the standard version of the model, for example. This is not as much of a problem, I guess, with more modern quantization techniques, but keep in mind that this is still something that you have to keep in mind. The second thing is this still has limited scalability, right? When we have 400 billion parameters, even if each of those parameters only takes half a byte, that's still going to be 200 gigabytes, right? And that's still going to be beyond the capacity of a single H100, for example. So this technique can help a lot, and indeed we still want to use this technique, but just overall, we do have some of these issues, right? And so the idea that we employ to kind of get over this is just use more GPUs, right? And so one of the ways of doing this is something called tensor parallelism, right? And this allows us to chunk our model over multiple GPUs, and that way you kind of have not infinite scalability, but you have much more scalability than you would have if you're just continuing to reduce the number of bits. So that being said, we can kind of go into a little bit of where this talk came from, right? What we notice is we've been getting a lot of questions along the lines of, okay, you guys support tensor parallelism in vLLM, pipeline parallelism, but really, what are the trade-offs here, right? What is the benefit of using TP in a certain case versus PP? And how does this impact the final performance? And this is not always super obvious or intuitive. And so this is, something that we've been seeing very commonly, and hopefully that's something that we can address in this talk. Okay, so I'll begin with a little bit of like a contrast with training and training regime, and to kind of give us a little bit of an idea of the challenges in inference. And so when it comes to training, this is kind of a situation where, it's very large scale, right? We often use a very large number of GPUs. We employ data parallelism, pipeline parallelism, tensor parallelism, potentially FSDP. And this is like a common situation where we see those like mega clusters, you could say, right? But with training, there's also a few things that are a little simpler compared to inference. The main objective that we have in training is throughput, right? We just want to get as many tokens as we can over a given period of time, right? And it's not really a dynamic workload either. Each step is kind of the same for training, right? So the complexity here kind of comes from both the parallelism that we have, as well as the algorithm itself, right? In training, we need to do both the forward and a backward pass. When we take a look at inference, we don't have that. We just have the forward pass, but the complexity kind of shows up in different ways. We have more like moving parts with inference. For example, we have the KV cache that we need to take care of. You also have to worry about potentially, if you're doing speculative decoding, draft models. And in the inference case, a lot of times we are really concerned about latency as well, right? We really want that shortest time to first token, something that we are concerned about there. And really, this is like a dynamic workload, right? Unless you're running, for example, offline inference, you're going to be running in a situation where users might be chatting with a particular model. You might have increased load at one point in time, decreased load at another point in time. And this is something that you need to account for. But when it comes to the scale, this is typically small, right? Since we're just running these forward passes, we can just allocate like a small number of machines to a single model, and then we can scale these horizontally depending on the load. Okay. And when it comes to large language model inference, there are a few like problems that we're trying to address. Right? The first thing is, as I mentioned before, the model cannot fit into a single GPU. And the second problem is that it can't fit into a single node. And the third is that you often have increased CPU overhead that comes from this. And the solutions to this are that vLLM provides are tensor parallelism, primarily to shard within a single node, pipeline parallelism, shard models across multiple nodes, and then we also have put a lot of work into the control plane of vLLM to optimize the CPU side overhead as well. And there are like some other things that we can get out of like doing this distributed inference. One of those things is decreased latency, and I'll touch on that a little bit later in the talk. Okay, just for a quick brief overview again of the vLLM architecture, and I'll just focus on this right side here. What we really do each iteration is we schedule a bunch of requests, and then we send it to this like executor. Right? So there's a wide variety of executors. For example, there's array version, multi-processing version, single GPU, and then for each of these hardware backends, you'll have a different executor. And this executor will manage each of the workers that we have, which are associated with a particular accelerator. And so it's this executor that kind of issues these distributed inference commands, I should say, to all of these workers, and then returns it back to the scheduler. And so this is primarily where this distributed kind of execution happens. That being said, let's go into a little bit more of overview of some of these distributed techniques. And we'll start with tensor parallelism. Right? So as we know, as models get bigger, one GPU is not enough, right? And indeed, multiple GPUs might not be enough. You might need to go to multiple nodes. But still, in this case, within a single node, you might have multiple GPUs that you can take advantage of. And so the question is, how do we parallelize the computation across these multiple GPUs? And so the answer that tensor parallelism provides us is to shard weights horizontally and then compute everything concurrently at the same time. So this is an SPMD kind of paradigm. And yeah, so that's what you can see on the right here. We're taking, for example, a model. Here it's just 4 layers for illustration. And then we're cutting up the model in such a way that each of the GPUs has a piece of each layer. And so we'll get into a little bit about how that works right here. So the first thing is we should go over a little bit of linear algebra just to get our minds in that mode. And so there's 2 main techniques that we employ with tensor parallelism. The first is column parallel. The second is row parallel. And these are kind of our building blocks for tensor parallelism. And they just rely on relatively simple linear algebra here. So I'll just get all of these on the screen here. So what we're really doing with column parallel is we're splitting the second matrix along its columns. And then when we compute it, you can see that we get 2 pieces of the resulting vector, right? And so these 2 pieces can just be kind of concatenated, and that's how we can recover the first result that we have here. With row parallel, it's a little bit different in the sense that we already kind of have this first vector split, and then we split the matrix along the row here. And then when we compute this, we get 2 separate pieces. But these 2 separate pieces just contain partial results, which we have to add to then get the final result. And so that's illustrated a little bit better here. We can see this like matrix here, it's split along this column. And then each of these sections here computes 1/2 of this final vector. And then we do what's called like an all-gather operation to concatenate these. And then same for row parallel. We have both of these split. We compute these like 2 partial results. And then we sum them together to get the final result, which we do with an all reduce. And this could be on like 2 GPUs. And so how does this work, for example, for an MLP layer, right? As we would have in, for example, Llama, right? And here it gets a little bit more interesting. This is a place where we can, where we have multiple operations going on. So we first have this up projection, then we have this activation section. And so the activation you can kind of replace with whatever you like there. And then we have this down projection. So all in all, we have 2 of these gem operations. And then we have activation in the middle. And this is how we get final result for our MLP layer. And so the way we can kind of employ some of those techniques is we can first employ column parallel here and split matrix A, right? And then when we get a result, we kind of get 2 different pieces. And then each of these pieces, since the activation will just operate element-wise, we'll then be able to get the output here also sharded the same way. And then finally, we have this final weight matrix that we shard along the row. And then when we get the result, it's really 2 partial results summed together. Right? So this is row parallel here, and the first one here is column parallel. And so what's the useful part about this is that we can do this over multiple GPUs. Right? And so this first half of matrix A can happen on the first GPU here, while the second half of the matrix or matrix A can be computed on the second GPU, right? And so we get our partial results. And I mentioned how on in column parallel, we would have to do like a all gather concatenate operation to get the final result. Right? But within the context of this MLP, we don't really need to do that, right? Because for our next row parallel, these need to be sharded anyway. So we can kind of avoid that whole synchronization right there. And so all we need to do is at the end, when we get these two partial results from row parallel section, we just need to all reduce these, sum them together, and then we got our final result on both of the GPUs. And so this is the fundamental kind of principle of tensor parallelism. And you can expand this to multiple GPUs. You just have to shard each of these matrices into more sections. And I'll kind of like stay on this slide for a little bit to kind of discuss some of the intuition that we can get just from understanding this technique a little further. Right? The first thing that we notice is that we have both of these weight matrices, A and B, sharded on both devices. Right? So both of these devices actually contain half of each of the weight matrices. So compared to a single GPU inference, this kind of gives us, a little bit, a few benefits, I should say, right? The first benefit is, given a large model, of course, now our weight, the space that we take for weights is basically going to be cut in half. Right? So if we had a 140 billion parameter model, now we're looking at 70 billion parameters on each GPU. And so what does that kind of do for us? I think the first thing is we can firstly fit the model onto the GPUs, or I should say serve the model in the first place, right? That's probably the biggest benefit that we get out of this. The second benefit is that the computation time is going to get a little faster, right? Since we're only computing half on each GPU. A third benefit that we have here is that because each GPU takes less KV or weight space, we have more space for the KV cache. Right? So in a situation where we have maybe 160 gigabytes available of GPU memory, and then we're serving a model that takes 140 gigabytes, we only have 20 gigabytes left over for that KV cache. Whereas if we add multiple GPUs, let's say we get double the VRAM, now we have each of those GPUs taking half the weight. That actually leads to a super linear increase in KV cache. So what you notice is even in cases where you can fit the model, let's say on one GPU or two GPUs, expanding it to more GPUs can dramatically increase your throughput in ways that aren't like super intuitive at first. So this is kind of a situation where you have to do the math a little bit, figure out, how much space you have for KV cache. If you divide the weights over multiple GPUs, how much KV cache you can really recover. And in some cases, it can be a lot more than what you originally started off with. But this has diminishing returns. And the third benefit that we have here, right, is that when we think about inference, oftentimes we have this concept of prefill and decode, right? As Michael mentioned in V1, we know we have chunk prefill, which I'll touch on a little bit later. We have that on by default. But in general, inference, it can be memory bound. That is the time that it takes to load the weights from GPU HBM to the compute, that could kind of be the bottleneck. If each GPU kind of has less weights to load, then you can effectively double your memory bandwidth. And this can really speed up your inference in terms of latency. The last thing I'll touch upon in this slide is notice that the data sent in this case, right, from one GPU to the other GPU, in this case, it's going to be a size, batch size times the sequence length times the hidden size. Right? And this is repeated also for attention. We just covered the MLP here. And then it's also repeated for every layer. So you can kind of see some of the trade-offs here. You do have to pay this communication cost. And so how do we kind of do this in vLLM? right? So both attention and the MLP layer uses tensor parallelism. And as I mentioned before, this executor kind of takes care of coordinating this distributed execution, kind of sends the exact same command to all of these workers. Right? As all of these workers go back to the previous slide, they're essentially doing the same operation. And this is our SPMD paradigm. Right? So it's a very simple implementation that we have. Okay, what about mixture of experts? Right? Mixture of experts, we have the situation where we have multiple experts, and we employ something called expert parallelism here to get this sharded across multiple GPUs. Right? And in this situation, each of these GPUs could have different tokens coming through them, and each of these tokens may need a particular expert. So we use what's called like an all-to-all operation to send the correct tokens to the correct expert, compute those, and then we do another all-to-all operation to recover them on the original GPU. So this isn't currently in vLLM. This is something that's planned, and stay tuned because I know a lot of people are waiting for this, especially for models like DeepSeek R1. Okay, so let's talk a little bit more about tensor parallelism in terms of the trade-offs. So I mentioned that this improves the end-to-end latency, and we do that by splitting the weights over multiple GPUs, and that way we have less to load, less to compute. And the trade-off for this is what you're paying is high communication overhead, right? But this can kind of be mitigated if you have good communication hardware. So if you have links like NVLink within a node, it's not as big of a deal. When it comes to specific workloads as well, for example, prefill heavy workloads, if you combine this with poor interconnect, even within a single node, you can kind of see poor performance, right? So I think I had a workload which I used tensor parallelism on I think 4 L4s, which don't have NVLink, right? And there's also prefill heavy workload where you could see more than 60% of the time was spent in these already used operations within prefills. So that's a kind of a situation where the rule is not as hard cut, right? You really have to think about it, maybe do some profiling to understand if that's going to work in your situation. And we also have this caveat that the attention heads need to be divisible by the tensor parallel size, or you have to employ padding in general. Okay, now we'll go to the next problem, right, which is multi-node inference. And so again, I'll bring up like DeepSeek R1, but there's also a problem for other large models such as Llama 4 or 5B, or the large Nemotron model as well. And so this is a situation where you need to have multiple nodes just to fit the model in the first place, right? And so what we do here is we employ this technique called pipeline parallelism, right? Because over multiple nodes, you potentially don't have as good of a communication link as you would have within a node, right? And what pipeline parallelism basically does is it splits a model into multiple sections. And it does this not by sharding across, I should say, it does this by sharding across layers, right? So each GPU will have multiple layers. And this is, as you can see, just kind of, it's similar to tensor parallelism, but it's done along a different axis, basically. And so the way we kind of do this in vLLM is we replace for each GPU, each of the layers that we are not computing with this missing layer. And then each GPU only contains the layers or loads the weights that it's supposed to compute. Right? And then we employ send receive operations. So you can think of over here on the right side, for one GPU, we have these 3 decoder layers. When we're getting a copy of the data from the previous GPU, what we'll do is we'll use a receive operation. And then once we're done with our computation, we'll then employ a send operation to send it to the next GPU. And you can kind of see some of the code that we use within vLLM here on the left side, which hopefully should make it a little more clear. But basically, what we're doing is like just sending data after computing each chunk on a particular GPU. So you can see how this is slightly different to tensor parallelism, where all GPUs are kind of working at the same time. Here we have a situation where it's kind of MPMD. Each like each GPU has its own set of weights that it's computing on that it is distinct from the other GPUs. And here, what you notice is that at the end of the decoder layer, what we're sending is also batch size by sequence length by hidden size, but we're only doing this once for each group of layers. And so we have a lot less communication than we would have with tensor parallelism. But there is like a price that we pay for that. Right? Okay, so pipeline parallelism, it does have a low communication overhead, but it doesn't actually improve end-to-end latency. Right? So with tensor parallelism, when we split the layers, we have all GPUs working at the same time. This can reduce the latency. Not the same case in pipeline parallelism. It's also much more complicated in terms of the actual execution of it, and I'll show you a little bit of that very soon. But this can also kind of reduce the efficiency of pipeline parallelism. We also have like reduced batch sizes, and I'll also touch on that in a second here. And one thing that we can also do is combine these techniques together. Right? Like I mentioned, these both operate along different axes. And so what you can do is use pipeline parallelism potentially across nodes, and then tensor parallelism within a node. Although this isn't like a hard and fast rule, as I mentioned previously, sometimes you'd want to use pipeline parallelism even within a node. In other situations, your communication is so good that potentially you can use tensor parallelism across nodes as well. And one of the hidden benefits of this is when we use tensor parallelism in conjunction with pipeline parallelism, we actually have each GPU sending a smaller amount of data. It only needs to send the data for its TP chunk. And so we can improve that as well by using combination of the both. Okay, and so I'll talk about a little bit about some of those difficulties that I mentioned with pipeline parallelism. The first thing is if we kind of use pipeline parallelism in a naive way, you can see is like for each GPU, it would kind of compute its set of layers. And then once it's done, it would stay idle, right? Until it again got, the next iteration to do. And so this is obviously not something that we want. It's a huge amount of wasted space. So what we really want is something like this, right? Where we have all of the GPUs operating all the time, right? And so this is really like the ideal for pipeline parallelism, but it's also not as simple to implement. Okay? And so the way we do this in vLLM is we have this concept of virtual engine or request group, where each of these request groups, for example, you can see this light red and this dark red be part of the same request group, kind of independent streams of requests, right, that are completely data independent. And the way we implement this within vLLM is we use multiple schedulers and cache engines to maintain this separation, as well as do load balancing. And so we launch all of these request groups at the same time, and we use locks in order to maintain that only one request group is operating at a time on each given GPU. There are some like hidden problems with this as well, right? When we divide it up in this way, we also split our KB cache over these multiple request groups. Right? And when we split it in that way, we can support smaller batch sizes. And so each of these, when we send these through the GPUs, is kind of like a micro batch, right? All four of these request groups together would kind of be the batch. And in cases such as decode, which I mentioned previously, is kind of memory bound, right? The kind of bottleneck there is moving the weights from the GPU HBM to the compute, right? It's the memory bandwidth. When we kind of split the batches in this way, your decodes could take much longer, right? And so this is kind of one of those things with pipeline parallelism that you have to really be aware of, right? Another thing to keep in mind is like I mentioned, these batching inefficiencies, but also the fact that different micro batches could take a different amount of time. Right? And so what this leads to is bubbles, which we want to avoid, right? Idle time on the GPU. And so we can use chunked prefill in this case, where prefill might take a long time, decode might take a short time. We can mix these together in mixed prefill and decode batches. And we can also ensure load balancing among request groups. So the way we ensure load balancing among request groups right now in vLLM is we split the KB cache over multiple um, request groups, but we do so evenly. Right? And so each scheduler kind of has a quarter, let's say in a 4 pp stage situation, each scheduler would have a quarter of the KB cache. And that would kind of implicitly balance it if our policy is just to send requests to the scheduler with the most KB cache available. So that's how we kind of handle the second one. In the first situation, prefill and decode, that's where we use chunk prefill. And so just an aside on chunk prefill, what we're really doing here is you can see here we would potentially have a situation where we have a prefill and then we have multiple decodes after that. Right? What chunk prefill basically does is it amortizes the cost of this prefill by only doing a little bit of the prefill. And then the rest of the prefill, it does with subsequent decodes, perhaps of other requests. And if you do this in the right way, you can improve your throughput greatly. Another hidden benefit of this is that it also gives you more KB cache space. So if you set your maximum batch size, I should say, or number of tokens in this mixed batch, you can basically make sure that nothing going through the GPUs is going to be bigger than that. And so those activations, the memory that you take to do computations within the inference step, for example, will be limited based on that parameter. Right? You won't have an arbitrary prefill of 100K coming through and just completely, like going over your memory limit. Right? And so when you do this, the vLLM is basically able to infer that, you can use more KB cache space, and this can help improve your concurrency as well. Right? And so you can take a look at the Sarati series of papers if you're interested in learning a little more about this technique. As Michael mentioned, this will kind of be on by default with vLLM v1. Okay, and just to show you, some of the implications of chunk prefill, right? And actually choosing a good chunk prefill size, right? A default might not be right for your situation, especially given like your prefill to decode ratio. So this is a situation where we had Llama 13B just from a while ago on 2 L4 GPUs, the long prefill and kind of a short-ish decode with a long or a large chunk size. And we can see some of these bubbles that I kind of touched on earlier that we want to avoid. But take a look at the same situation where we have a smaller chunk size. Right? Here we kind of have a very smooth, no bubble kind of situation. And we're able to amortize that prefill over many more decodes. So this is an example of where I think in this situation, I saw like maybe 20% improvement, but choosing that chunk prefill size carefully can really help your deployments. Yeah, and the final consideration is that potentially different GPU groups have different like they take a different amount of time to execute their layer group. This we can kind of or implicitly take care of by splitting the layers evenly over each of these GPUs. That being said, like for some of these models, kind of the initial stage and the final stage can take more time. So this is not completely avoidable without some very careful tuning and hacking, basically. But this is something to keep in mind as well. Okay, so I'll kind of conclude with a little bit of a summary of some of our discussion topics. And we want to basically use TP and PP together in situations where it's applicable, but not keep it this as like a hard and fast rule. Kind of do some experimentation and figure out, what works best for your situation and your workload. You do want to use chunk prefill, especially when it comes to pipeline parallelism, but you don't want to set that chunk prefill size too large, and you want to take advantage of the amortization over multiple batches. And you also don't want to set these settings arbitrarily. Like what works for one deployment, one workload, one set of hardware is not necessarily going to work for another set of hardware and workload and constraints. And so that's where these like playing around with some of these settings comes in, and being able to set these parameters based on that. And so you can see here we have an example command for serving DeepSeek R1, where we set both the tensor parallel size, pipeline parallel size, as well as enable chunk prefill. And you should be kind of well equipped to employ some of these models yourself. Awesome. Yeah. So in conclusion, you support tensor parallelism, pipeline parallelism. You have to consider the trade-offs carefully, and stay tuned, especially for new developments such as expert parallelism and V1 as well. Yeah. So that kind of concludes my section of the talk. I'll hand it over to Tyler, and I'd be happy to take any questions as well.
Yeah, thanks a lot, Morelli. I think we got a lot of good questions out of that already in the chat. Maybe a good starting one was from Rajesh. What was that tool used for profiling on the chunk prefill slides?
Yeah, sorry, I just went over this.
Sorry. I think it was NVSite, yeah? Or
Yeah, so this is Nsight Systems. So this allows you to kind of take a look over entire workload for a particular section, and you can see all the kernels that are launched. So it's really good for taking a look at not only the times for different kernels, but also some of this, like, for example, CPU overhead that you might like also wish to kind of fix.
Right. I think another one was, sorry, there's been quite a lot of discussion. I'm not sure. I can't find it right now. If anyone wants to speak up or ask questions, feel free to now.
Yeah, I had a question. Nice to meet you, by the way. With the disaggregated prefill and decoding, I was looking at some of the code for Mooncake, and I saw that it uses Pi and CCL. I'm just wondering how much you see variation in terms of like the latency of given switches, and so obviously of like the NICs. Does that impact scheduling a great deal, and how do you handle the fact that it obviously runs on different hardware?
Sorry, just to like understand that question, are you more so concerned about Pi nickel or about the different switches? Would you say?
I guess not so much in the software, more in just the question of obviously just the RDMA operation having to traverse different hardware using that API.
Yeah. So okay, so I can speak like kind of generally, maybe not specifically about RDMA, but like within a single node, for example, when we employ like, for example, tensor parallelism. I mentioned that for L4s, we don't have NVLink available, and we go over PCIe. And so no matter what you use here, whether that's going to be like Pi nickel, whether you use like torch distributed, which again is going to be built on nickel, you are going to see kind of a larger latency for that communication time in tensor parallelism. That being said, like within vLLM, we have this kernel that does all-to-all and GPU all reduces within a single node, and this will be turned on in certain situations. For example, when you have NVLink, everything's well connected within a node. You'll have that kernel available to speed up the communication latency. Not sure if that quite answers your question, but
Yeah.
hopefully that gives a little flavor.
My question was more on, so it does answer the question on the NVLink and NVSwitch. I was curious on Mooncake's like multi-node, one particular node handles like a portion of the model, so the decoding phase, the other one does the prefill. And in their particular white paper, they seem to be more touching, rather than the NVSwitch, for DMA operations between VRAM to VRAM within the device, they traverse the RDMA fabric. So they'll use like Mellanox Pure Direct, or I guess we're calling it GPU Direct at this point.
I see. I'm not as familiar with disaggregated prefill. Not sure, Michael or Tyler, if you guys would have something to add on there.
Yeah. Sorry, this is with respect to like how does the interconnect affect like latency for disaggregated?
I'm curious just because so I was at Cohere before and we were using Rocky interconnect, Rocky V2 on Arista switches with I think like a whole pile of 400 gigabit per second switches. And we saw obviously like higher latency than you would get on, like if it was CoreWeave with InfiniBand, for example. And I was just curious if you have like a multi-node architecture where you have one like discrete node actually handling prefill and another discrete node physically handling like the decoding, and you'd have to traverse the fabric. One would imagine that the scheduling would become more difficult just because of the fact that it's not like NVSwitch is NVSwitch. It's like now you have multiple different fabrics that you have to handle. So hence I was thinking might be good to have some sort of abstraction in the scheduler that can know about the hardware, or maybe test the hardware and make decisions on how to move the KVs around based on that.
Yeah, I think that's a fair point. A lot of the work on the disaggregated prefill kind of like starts with this claim that you can overlap, and most people like try to do so. So one node will do a prefill, and then while it's doing the next, kind of iteration of generation, it will take the KV cache and, transmit it, send it to the other vLLM instance that's designed to decode. And I think this pretty much holds kind of like for current LLMs. This might change for especially like chain of thought or like when you go to really, really long context, this might not hold anymore. But kind of like the conventional thinking today is that, yeah, you can just overlap these. So, the cost of transmitting the KV cache is not so high.
Yeah. I just wonder about like fabrics, for example, with oversubscription, where sometimes people don't design them exactly to the reference architecture with NVIDIA. We had like no choice on the switches that we used in Oracle. They just did an equity for a compute deal with us. So if they happen to be oversubscribed at all and we started losing packets in flight, or they showed up a lot later than they were supposed to, one would imagine with this kind of like disaggregated model that if some packets are in flight and they don't arrive exactly when they're supposed to, it might slow the system down.
Yeah, interesting. If you have any link to that discusses the hardware, I'd be interested in taking a look.
It's super non-public. But I'd love to talk to you.
Okay. Yeah, thanks.
Arthur, if you want to reach out to me or Tyler or Michael or anybody here, we're happy to have a, off the Zoom conversation.
Absolutely. I'd love to talk to you guys.
Yeah. And like DM on the vLLM Slack as well.
Yeah, 100%.
Does anyone know for multimodal distributed inference, multi-node, what's the communication protocol Ray uses? I'm not familiar, but Tyler, any chance you know more about Ray?
No, sorry.
I do believe Ray can use like nickel under the hood. I think that's one of the newer developments, but yeah.
Yeah, but it supports like multiple things. It's like
It does, yeah.
it's just like regular inter-process communication.
Yeah.
Yeah, well, we are over time. So maybe we should close things out, but definitely if there's like leftover questions, happy to stay on and just like chat about things if there's interest. So Murali, could you just skip to like the second to last slide?
Yeah.
you're already up there.
This one here.
The next one. Yeah. So yeah, just to close things out, or sorry, the one before. Thanks. Yeah, we're always happy to see you here. Thank you for being good users and, people of the community. Of course, if you want to contribute to vLLM, please check out the issues or PRs and features you're interested in. Come in the Slack. Let us know what you're interested in. This helps drive priorities and development on what we're going to work on. Check out also the roadmap for Q1 at roadmap.vlm.ai. And give us feedback there or in the Slack as we say, and also let us know if there's anything within office hours we can do this year to better serve you. We have a lot of ideas of what we're going to do this year and hope to do a lot more meetups, but happy to take criticism. And later today I'm actually giving a talk if you're in San Francisco at a meetup on a full stack open source AI. We're going to cover from chips to apps on how to get started with open source AI with a few other companies. So yeah, that's cool. And we're hiring for vLLM engineers, and I'm sure Sentinel is hiring as well if you want to work with Morale. So yeah, that's all. Thanks everyone for joining. And thanks Morale for the great presentation. Yeah, we really appreciate you coming in.
Happy to stay on for any questions as well.
I think there is one question from James Westbrook about the production stack project. James, do you want to ask, or Michael, do you just want to read the question?
Yeah. So it's just a question about the new vLLM production stack project or LM stack. I think unfortunately we aren't the right people that worked on that. But I think definitely please go in the vLLM Slack and just ask openly in the contributors or questions channel. I think we have those people in the vLLM Slack, and they'd be happy if you have interest or want to understand more parts of that as they're working on documenting it and building out more features. It's pretty simple to start with, but we hope it'll be a good reference architecture for the community to use and build on top of. Yeah. But appreciate the interest. Unable to produce vLLM dashboard result V0 on A100. Yeah, talk to us in the vLLM Slack on that. We're happy to debug performance things. I think the performance dashboard has been under construction for the last couple weeks. Yeah. But it seems like we're probably pretty good here.
Right. Thank you everyone so much. We'll see you on February 6th for an update on multimodal inference in vLLM v1.
Awesome. Thanks everybody. Take care. Have a good week.
You